field measurement. FOSS1 did also ask me to talk a little bit about the history of scope, so I'll very briefly go into that as well. Advance here. So next month, scope will celebrate 11 years. Just as an aside, I would prefer if people just have questions as I'm talking, please interrupt. Otherwise, I defer to FOSS1 as to how he wants to run this. So 11 years ago, Scope was spun out of the ETH. This is a company which is bootstrapped out of the ETH with funding like Swiss government, small company funds, early customers, etc. And the evolution of a small company like this is pretty interesting to see. We started out, this is the first product that Scope produced. First customer, I think, was to the KCL cardiac group in 2011 or 2012 even. You can see this is a prototype, right? So what you get as you move on as a company is you need to make real products and you need to industrialize and kind of make things easier to use. And this is a journey that we're still on now. So this has been the second generation dynamic field camera. You can see it's a bit more professional looking, right? So these are the steps that we continue to go through. Where we are now, here's just a screenshot of our website. We try to position as a partner in scientific MR imaging. So coming alongside methods developers or even very technically oriented neuroscientists to do MR imaging better than they could before. And you see an image here of our 3T NeuroCam, which is our receiver coil with integrated field sensors, again, designed for 3T. So moving on, I'll take you through this outline here. Starting out with just an analogy of how we make images, and then you can read the outline. I'll just continue down through it. So first, making imaging in general is making a representation of an object, and in optics, we would consider that the object, the light from the object goes through multiple transformations by the time it's recorded by the imaging system. It can be a chromatic aberration, so we know that a light passing through a lens of different wavelength is slowed at a different rate, and therefore the focus is different. If you don't track this, you'll have artifacts in your image. If you make a lens, maybe you say you naively make a lens as a sphere. Again, light passing through different points in the lens will focus at different points, and you again get a blurred image. Multiple cascading effects can result in distortions in the image, which you have to measure these distortion effects and take care of it if you want a representative of your object, which is closer to the truth. So how does this relate to MR? Well, in MR, we have a relatively involved image formation and encoding process. If we look at my nice low-res image of a scanner, we have a variety of systems here. The magnet, or the main field itself, is responsible for the polarization of the sample. We assume it's stable over time, and we assume it's uniform. If not, we have to have some extra information to take care of that. We assume the gradient, or the electromagnetic system within the magnet, we assume that that's linear over our imaging field of view. We assume it's repeatable, so that gradient pulse 1 is the same as gradient pulse n if you've programmed it to be. And we assume that whatever we play out is exactly what we've programmed. Now, there's various levels of these assumptions and how true they are. And finally, for RF, we have to excite the sample and we have to read it out again. And so we usually assume, for example, at 3T, the B1 plus field or the transmit field is uniform. We assume that, again, RF pulse 1 is the same as RF pulse n as we go through our entire sequence. Using all of this information, we play out this sequence, or this pulse sequence, as we normally call it in MR, of gradient and RF waveforms. We do some image reconstruction process, and then we end up at an image. Starting a few decades ago, we learned that we can take the sensitivity maps of the receiver coils, of these phased array receiver coils. We can use this additional information to correct for some of our shortfalls in information. Maybe we have some shading across the image we don't like, but we know the B1 minus or the received sensitivity profiles. We can then correct for that during our image reconstruction process. Starting in the mid-2000s, or 1999, I guess, we decided we can undersample images and then reconstruct using sense or graph or whatever your favorite parallel imaging method is, using this information. So we have extra set of information to compensate for something that we miss during our acquisition. Similarly, if we have a static delta B zero field, the person itself or the object itself does perturb the imaging. If we have information about that, we can also compensate for that during the encoding process. So this is information we're relatively used to in MR incorporating to our image reconstruction process. Well, again, it's not that simple. My undergrad physics professor just told me that as you learn more and more about the world, you really end up telling yourself smaller and smaller lies about how everything works. And that's very much the same with MR. As you learn more about the system, you realize that there's more and more lies essentially that you're believing about how you made an image. But so that there are many sources of these issues, of these encoding errors. On the time scales of a few microseconds, you can have just gradient delays. Different cable lengths from the amplifier to the gradient coil itself can cause different delays from when you program a pulse to start to when it actually happens. The gradient coil itself, it's a big magnet operating in a strong magnetic field. So Lorentz forces are quite strong and they can cause the whole gradient coil to shake, which also then changes the impedance of the coil at different frequencies. So you can have different distortions of your encoding field based on this, all the way up to, as you're pulsing an electromagnet inside a cryostat, you can build up heat in the cryostat or in the gradient coil itself, which then causes the magnet field to drift over time. So what we're adding is the measurement of the encoding process to this image reconstruction, taking into account an additional set of information in order to form an image. Now I'll introduce a term called complete encoding. I know it's not going to be complete because there's always something we won't take into account, but adding to this information we already have about our sequence, we then can measure the case-based encoding terms in real time with a set of tools. Here you'd have what we normally think of as case-based, parameterized in kx, ky, and here we're showing a spiral. If you also consider the center frequency or the zeroth order, we can measure that as well, and then all of these additional terms. And we're doing this with a set of additional sensors in the scanner. Really, it's adding a subsystem to the scanner. You have the magnet gradient RF subsystems, and then you can have some sort of encoding measurement device. So how do we do this? We measure these with little NMR experiments. So each probe, as we call them, has an NMR active sample, a little coil around it, a susceptibility matched casing, and some tuning and matching electronics to be able to give you a point FID measurement. We take an array of these probes. Here we put it roughly around a sphere. And then if we have a point FID measurement, we have a point field measurement. And then if we know the position and off resonance of each of these positions of each of these probes, we can then calculate based on Maxwell's equations the field and predict the field inside that sphere. How this works in practice: if we excite and read out a probe in the presence of a magnetic field, we get an FID, or free induction decay. If we then pulse a gradient, we can see that we dephase the probes, and then if we go back, if we rephase that same gradient, we then get back to our standard T2 star decay curve. We extract the phase information from these FIDs. Remember, extracting phase information from an FID is really calculating the field evolution at that particular point. Knowing the position and local off resonance, we can then fit that field to a spherical harmonic model of the field. So here we've, with 16 probes, we can fit up to a third order spherical harmonic model. And then these resulting fits show the evolution of each of these case-based coefficients over the course of the scan. So here we're showing over about 18 milliseconds for this short bipolar blip, all these field components, including here's the concomitant field line. I have to mention that since I was mentored by Dr. Bernstein for a while. How does all this work together? Well, if we have the encoding information and we know that there's a bunch of encoding perturbations going on, for example, in diffusion imaging, you can see the results here. So what you're looking at is an image of a phantom. This phantom is not moving in the scanner. And the time direction that it's scrolling through is different diffusion encoding directions. So maybe we have plus X or plus Y or plus C minus C in diffusion encoding, but the readout module itself is the same. These field terms are responsible for this characteristic shearing and warping you'll get in diffusion weighted EPI. This comes about because we have different diffusion encoding directions, and each of those directions has a different phase behavior in all these different terms. This is caused by the construction of the system. Now, we can account for this if we change our reconstruction model from our standard phase term up here, taking into account the linear k-space terms, to a more generalized model where we account for all the different spatial orders. Once we do this, if we reconstruct with that additional information accounted for, we can then build an image which, accounting for those additional terms, is now more stable. So we've just removed one assumption from our image reconstruction with an additional set of information that we have. See, this is going to be quite a quick talk. Hopefully that's all right. We can apply this to some unique systems. So at the ETH, they do have a insert gradient system here. The specifications are if you run it in different modes up to 200 millitesla per meter and quite a high slew rate. But it doesn't quite behave as you expect. So in order to characterize the system and understand what it's really doing, we did quite a lot of measurements using some field measurement tools. And in the end, if we know our encoding dynamics, we can get down to some quite high performance results. So an echo time of 19 milliseconds. This is both using these strong gradients and a spiral readout compared to an EPI readout. Adding additional information in this application. So if we do a 0th and first order model, so this is akin to just knowing k-space as we think of it, kx, ky, kz, and center frequency. We do need to add additional information, but then also keep track of concomitant fields. So these are the also called Maxwell terms, which arise from linear gradients as you pulse them, and they're unavoidable. Just another shot of this 0.7 millimeter in plane resolution produced by this system. Another fun thing you can do if you have a really fast gradient system. Here we did a 30 echo spiral scan at this gradient mode and measured the encoding through the entire process. And you can do things like relaxometry in a single shot. So if we take all these images, all required in 70 milliseconds, you can put a little ROI in gray matter, white matter, CSF, and do some relaxation measurements. You can apply this also to diffusion imaging. So if we go back to a bit of more basic example, doing twice refocused spin echo EPI was the gold standard for getting eddy current distortion free EPI images for a time. And we then moved to single refocused spin echo EPI as different sets of calibrations became available on commercial scanners. So going to a single refocused spin echo EPI means that you can move your echo time closer to your excitation, and then you're higher up on your T2 star decay curve in your signal. Well, if you can move that TE even closer to excitation, or have an even lower TE and even higher SNR. So here, if we move to spiral from EPI, we're then even getting a bit higher spatial resolution. And then just showing the combined images based on a few different diffusion directions. We also can show this empirically, that the SNR is higher, controlling for all the other factors, same receiver coil, etc. Now this is great. I'm showing that you can reduce your echo time, you can increase your signal to noise, but why doesn't everyone do spiral diffusion weighted imaging? So here we have our excitation, we have our statistical tensor diffusion prep, and then we're reading out a spiral. It's for the same reason that I was showing earlier. These big diffusion lobes, they throw off eddy currents, which are quite strong the closer you are to the diffusion lobe. So it depends on the time constant of those eddy currents. And what I showed you before was all these different phase terms kind of arcing up right around this diffusion lobe. And here you'll notice you're at the k-space center, or kx, ky equals 0, where there's the most signal. So you are then putting your area of image acquisition where you have the most signal right next to your most perturbed encoding field. That's why it's really difficult. So if you do this and you don't take anything into account, your B0 spiral image doesn't look great. Now, I grant you there are other ways to correct for this as well. But then your diffusion weighted images look pretty terrible as well because you are corrupting the acquisition. So if you add an additional field measurement device or add additional information about what is exactly going on at this kxky equals 0 portion, you go back to this where you take into account in your signal model that additional information, and then you can clean up your image by accounting for the actual encoding which has gone on in the system. So that's at 3T. There's different extensions to 7T, up to and including doing multi-dimensional diffusion prep. So I showed you a straight pulse gradient spin echo acquisition before, but what if you want to do something kind of more fun and get more information about the anisotropy of your system? So the micro FA map, as it were. These slides are from our customer in Montreal. The more complex your diffusion encoding gets, the longer your echo time gets, the lower your SNR is, and the lower resolution you're forced to live with. This is even worse if you move to 7T, where you have shorter relaxation times, and you need to acquire faster in order to maintain image resolution. So what they've done is a spherical tensor encoded experiment with an echo time of about 70 milliseconds. And this is with a spiral readout, and then they did a recording with the field camera. The comparable readout in an EPI would have been about 110 milliseconds with quite a bit reduced residual signal because of that. And the different corrections that they did. So if you have this nominal trajectory where you just trust the scanner to play out exactly what you tell it to, and you have no static delta B0 correction, you can see the results. Moving to a more traditional, just adding a delta B0 correction. This B equals 0 image maybe doesn't look so bad. That's because you don't have the additional corruption from your large gradient activity happening right before the readout, and then that's borne out with these diffusion weighted scans. Only after you add all this encoding information, you get a result where you can resolve small details of the brain. Now, in general, other things you may want to do if you have additional information about your acquisition in 7T, look at this high resolution scan from a Philips system from a few years ago. Looks okay. I'm not a brain expert, but okay. But if you add additional information which accounts for the patient breathing in the scanner, you can then clean this up. So going back and forth, now you can mention, yeah, there's some signal coming out where it shouldn't be. There are parts of the cortex which are now better delineated, and there's less shading in general. There's the difference image. And one more example here, and I like this example because it shows this bit of shading here, which again, I'm not a 7T imaging expert, but a lot of times when we think of shading at 7T, we immediately go to B1+, and then we have to solve this with PTX or some other kind of dielectric pads or something. When it turns out that the issue here was echo shifting due to field instability due to patient-induced field changes at the head. So the chest wall motion or moving your hand to your chin or something like that. Additional things you can do at high fields is spirals for fMRI. So these are then inherently registered to your anatomic priors for a nice overlay, given that you have absolute information about how the image was encoded. Next, you can look at whether you want to monitor that acquisition or simply build a model, build a model of your system, an impulse response function, and then predict how your system will react. And you can get quite a ways, quite a bit of improvement, just understanding really how your system behaves in an ideal sense. So finally, wow, I really burned through this. Finally, just an overview of what we offer to get to these states is we have what we call a clip-on camera. So adding field sensors to an existing coil. So here's just an example of there's a wave Kuiper moment issue where you're missing a gradient moment. It's not an RF shading issue. There's a trajectory problem. We have a version of this which is particularly adapted to the Siemens single channel transmit system. So this is built to fit directly inside that coil and have all the probes in the right positions and to be able to install and deinstall it relatively quickly and then fit on the table. We offer a reconstruction software to be able to take the image data and the data from our system, combine it together and generate an image from that. So this is an offline recon, but it's what we're able to offer. We have our, maybe we call it the classic field camera, the original product to use for measuring how your system is performing or doing your pulse sequence programming, debugging. As an example, if you're doing an SSFP sequence and you're realizing your banding is just out of control, if you would measure this, you can maybe see that there's a drift up and you're really not in steady state. You know, there's something in your system going on where you would then need to add maybe a sequence correction to make that work. Then finally, our 3T receiver coil with integrated field sensors. So kind of tying everything together, doing the RF reception, which then goes through the MR system, and then doing the field sensing, which then goes into our system. You can see that we've designed this for brain coverage. It's a brain coil, not a head coil. And comparing spiral to Cartesian. So we would like to say that we're able to enable spiral imaging to be done well because we know exactly what's happening in the scanner. And then if you enable spiral imaging, then effectively your parallel imaging is then done in two directions simultaneously, rather than in EPI, for example, you have to pick an acceleration direction, and then your coil sensitivities are not optimally used. We integrate this into the system by interfacing the receiver with the vendor spectrometer, and then we have our own acquisition system to acquire the field dynamics, and then combining these together in our reconstruction. So I would have to say I flew through that quite quickly, but I would be very happy to take any questions, and I have a pile of extra backup slides if there's anything that you wanted to go through.
Thank you very much, Paul. So I don't, oh yes, Chuck has some question, please.